Assistive Robotics is developing technology to help people overcome mobility challenges. And the goal here is really to let them live a fulfilling life and do the activities that they want to do and connect with their community and their loved ones. So artificial intelligence and machine learning really impacts our work in two different ways. The first is understanding and sensing movement metrics that are hard to capture outside the laboratory. So we can use wearable sensors with AI and machine learning tools to really estimate these hard to measure signals. For example, how many calories you burn when you exercise, or the loading in your joints, or these very specific metrics for movement. AI and machine learning also helps us advance our assistive robotics technology and really around personalization. So everyone's unique, and this challenge of integrating a human and a robot seamlessly requires us to tune the system to the needs of each user. And so we can use these AI and machine learning tools to do that very effectively. So smartwatches estimate the calories that you burn during exercise with about 40 to 80% error, and this is really surprising. And it has to do with what sensors they use to estimate this. For example, they often rely on heart rate or wrist motion, but actually biomechanically, the energy that you expend during movement like walking or running is due to the muscle activity in your legs. And so we can try to build better models by capturing relevant information to your leg motion. And so for example, we use a smartphone in our pocket to really improve this accuracy because force F equals ma, this is a fundamental physics law, and the force that your legs produce is related to the acceleration of your leg. And so by measuring that acceleration, we can sort of back out with machine learning models and wearable sensor data what is actually going on in your muscle activity. So by having biomechanically informed and feasible models using AI, we can really try to capture these methods accurately. Sometimes they're counterintuitive things like your heart rate. You'd think it would be very related to energy expenditure, but actually it varies dramatically with sleep or fatigue or caffeine. And so for most activities like walking, it's not very accurate. It's confused by all these different factors. And so we need really direct biomechanical measures. And that's a big challenge in AI, is how do you make sure that your model is representative of what you're trying to capture, right? And so we often try to use everything we know about biomechanics and provide good data to really give the model a chance to succeed and capture something meaningful for our health or for our mobility. One example of our assistive robotics work is developing exoskeletons, and so these are motorized systems. One particular device is an ankle exoskeleton. Effectively, it's a motorized boot that helps you push off as you're walking and provides sort of a spring in your step. And this system, the big goal here is how do we tune the assistance so that it works in harmony with the person and really reduces the effort it takes them to walk. So for older adults, you can imagine reducing fatigue and increasing speed. And so we developed a machine learning model that estimated the person's effort based on the IMU data, or the inertial measurement unit data, from the ankle exoskeleton. So as they moved, we tried out different ways to assist the person, different controlled profiles. We saw how effective it was, and then quickly this algorithm figured out what's most effective for each person. Personalization with machine learning and AI can be a really effective way to accelerate and improve the outcomes we see with assistive technology. We're at an exciting point where we have devices that are quite capable, and we're starting to see devices be produced at large scales and become more like consumer products. And this AI research in terms of personalizing assistance and tuning robotic assistance to individuals is showing really incredible effectiveness in many different categories for different populations. There's more work to be done in terms of improving these for safety and deployability and robustness, and also trying to accommodate all the different things that people care about. We're starting to go from the lab to beyond the lab and to many different activities. So rather than just for, walking on a sidewalk, be able to accomplish many more activities and adapt to those readily, like going upstairs, going downstairs, performing more dynamic movements and moving towards, sports or really complex motions. But we're moving in a promising direction, and we're seeing big benefits, which is really exciting. I see assistive robotics really having an explosion in the next 5 or so years. I think soon you'll be able to go and for example, take your grandparent or loved one who maybe needs an extra boost in their mobility. You'll be able to go to Target or some big store and purchase a device, put it on. And the really exciting piece is using AI and machine learning, these devices will be able to personalize assistance to each user. So they'll put on the system, they'll walk around, and it'll quickly tune and figure out what's the best way I should assist this person to give them, a boost in their step, to reduce their fatigue or increase their walking speed and allow them to do the activities that they want to do. And so I see that as, a really exciting jump both for our research, but also for translation to patient populations and to people that we care about and having real-world mobility benefits.